going to start with question 9. So question 9 is a maximization slash minimization question. And in this question, it says a box with a square base and an open top must have a certain volume. Find the dimensions of the box that minimizes the amount of material. So for these questions, the best idea is typically to start off with a picture. So I'm going to start off with a picture of a square box. And from here, it has a square base. So we know that this is length x, x, and this is some height h. And what it's asking us to do is it wants us to maximize the amount of material or minimize the amount of material given it has a certain volume. And there's no top here. So what we're going to do is if I look at the dimensions of this box, the surface area of the box and the volume of the box are the two main pieces. And the surface area, each of these sides, so h times x, there are 4 of them. So it's hx times 4. But then I also add this base, which is x squared. So that's my surface area. Sorry, let me label that surface area. And then I have my volume. And the volume is hx squared. And what we'd like to do is we'd like to, given that the volume is equal to 32,000, we'd like to minimize the surface area. So we'd like to, let me go back to the appropriate section. We'd like to minimize this expression here. So now that we have it as an equation with some variables, we need to convert it to an equation of a single variable, which means we need to use our volume to make h a function of x. And if we look at our volume, we've got h equals, down a little bit, we've got h x squared equals 32,000, or h equals 32,000 over x squared. Now that we have that, we're able to update our surface area equation. So our surface area equals 32,000 over x squared times x times 4 plus x squared. And at this point, what we want to do is we want to determine the domain for this shape. So for this shape, we have specific domains that we must satisfy. So first thing that we have is that our x value, the length of x has to be positive. So we know that x is greater than 0. And we know this because it has to have some volume. But this is also really nice because now we don't have to worry about dividing by 0 with x equal to 0. So we can simplify our surface area equation. So our surface area equation equals 4 times 3,2,0,0,0 over x. I'm going to change this to a circle here. Plus x squared. And we'd like to maximize this equation. So now, now that we've defined our domain, we're going to maximize this expression over, or sorry, we're trying to minimize this expression. So we're going to minimize this expression over the domain. And to do this, we're going to look at its derivative. So we're going to take the derivative of the surface area, and this is equal to negative 4 times 3,2,0,0,0 over x squared plus x plus 2x, which is equal to, and now I'm going to get a common denominator. So it's going to be x 2x cubed minus 4 times 32 times 1,000. And I'm going to separate it a little bit all over x squared. And now I'm going to factor out a 2 to give us 2 bracket x cubed minus, and this gives us 4 times 16 times 1,000 over x squared. And again, because we're looking for our critical values, by factoring it, we can easily determine what those critical values are. And simplifying a little bit more, we get 2 bracket x cubed minus 4 cubed times 10 cubed over x squared. And now, if we recall, our critical values are when our numerator equals 0 or our denominator equals 0, and we're within our domain. So first, looking at when the numerator equals 0, x cubed minus 4 times 10 all cubed equals 0. Well, this implies that x equals 40. So one of our possible values is 40. The other possible value we have is from the denominator of x squared equaling 0, or x equaling 0. But this is not in the domain, so we can ignore this because it's not in the domain. So this means our only potential value is 40. Okay. And now we have to determine, so we have our critical value of 40, and we have to determine, is this a minimum? And to determine it's a minimum, we can do one of two things. We can either use our sign chart or a first derivative test. I'm going to be using the sign chart to use the first derivative test instead of using our second test. So for the first derivative test, I have the point 40, and then I have 2, I have x cubed minus 40 cubed, and I have x squared. Now, 2 is positive everywhere. X cubed minus 40, leading term is positive, it changes at 40. And x squared is positive everywhere, which means I'm positive and negative, meaning I'm decreasing and increasing. This tells me that 40 by the first derivative test, 40 is a local. Now at 0, I'm undefined, and this is true for everything above 40 as if its only value. So now as f of x is always decreasing until 40 and always increasing after 40 is a global minimum. So we have a global minimum at x equals 40. So now what we can do, now that we know where the global minimum is, the last step is to figure out what the question was asking us to do. And it was asking us to find the dimensions of the box that minimizes. So we found the x value that minimizes. We now need to find the dimension. So because the x value is 40, we can use our volume to find the dimension. So we know that x equals 40. And the question is, what is h? So h equals 32000 divided by 40 squared, or h equals 20. So I divided two of the zeros to cancel out the 2 10s from 40, and then the 4 I divided 32 by 4 twice to create 8, and then finally 2 to give us a height of 20. So my box dimensions are 20 by 40 by 4. And these are the dimensions.